Welcome to Ordinary Differential Equations, Lesson 34. Use of the Frobenius method in the case of a double real root of the indicial equation. In this lesson, we will find Frobenius solutions to this differential equation. So we're looking at this differential equation, and we're going to look for a Frobenius series. We're going to, for a solution, let's let y equal x to the r times the power series, sum k goes from 0 to infinity, c sub k times x to the k. We can multiply these together, and instead of having x to the r out here and x to the k in here, we can just put x to the r plus k inside our summation. So then let's look at certain things that we have up here. Let's look at this term first. 4 minus 2x over x squared times y. We can write that as 4 over x squared minus 2 over x times y. Now, 4 over x squared times y is equal to this, minus 2x times y is equal to the stuff over here. If we move on to this term, we can proceed similarly. First of all, if y is this infinite series, then differentiating it term by term, we get that y prime is this infinite series. And then let's use that to evaluate 5 plus 2x over x times y prime. We can rewrite this as 5 over 2x plus 2. 2x over x is just 2 times y prime. Okay, now 5 over x times y prime is this series. 2 times y prime is this series. Let's move on to this term. If y was this series over here, differentiating term by term gave us y prime. Differentiating y prime term by term will give us the second derivative, y double prime, which is this stuff right here. So at this stage, we have series, infinite series, for each of these three terms in this differential equation. So we will substitute them in. So let's do the substitution of those series into this differential equation. Y double prime is this series, plus 5 plus 2x over x y prime is sum of these two series. Plus 4 minus 2x over x squared y is the difference of these two series, and the whole thing equals 0. Now, we look at this, and we would like to solve for these coefficients, C0, C1, C sub 2, and so forth. So what we need to do with this is some re-indexing and combining like powers of x. If we do that, and I'll leave the algebra for you to look at, we can get this in the following form. First, the C0 excuse me, the C0 term is going to be the quantity r squared plus 4r plus 4 times C0 times x to the r minus 2, plus, And then here are the rest of the terms. Sum k goes from 1 to infinity. And here we notice that we have this stuff times c sub k plus this stuff times c sub k minus 1. And all of this is a coefficient of x to the r plus k minus 2. And so if this series equals 0 for all x in some interval, then this coefficient of x has to be 0, and all of these coefficients of x to the r plus k minus 2 also have to be 0. So if we look at this first term, we notice that we can write it as r plus 2 squared times c naught times x to the r minus 2. And if that equals 0 for all x, and recalling that in the Frobenius method we have that c naught is not going to be 0, so that means that r plus 2 squared has to be equal to 0. So r equals 2 minus 2 is a double root of the indicial equation. To find the recurrence relation, let's remember that we found out that r has to equal minus 2 from the indicial equation. And also, each term in the power series has a coefficient of x raised to some power, and that coefficient has to equal 0. So knowing that this thing up here has to be 0 for all x in some interval means that that coefficient of x to that power, this stuff right here, has to be 0. Now, if you look at this carefully, you'll see that we have something here times c sub k plus something here times c sub k minus 1 equals 0. We can subtract, for instance, this from both sides of the equation, and then we could divide by this quantity here to solve for c sub k. But first of all, let's notice that we have something squared plus 4 times the same thing plus 4 here, and this is equal to r plus k plus 2 quantity squared. This binomial squared gives us this term right here, this factor right here. And so if we notice that, we can rewrite this equation this way, and then we can, as I mentioned, solve for c sub k by doing a little bit of algebra. Subtract this term from both sides and divide by this factor here, and we get c sub k equals this fraction times c sub k minus 1. Remember that we know that r has to be minus 2 from the indicial equation, so we can plug in a minus 2 for all of the r's here, and this simplifies to 2 times k minus 2 minus 4 over k squared, and that simplifies a little bit more to minus 2k minus 8 over k squared times c sub k minus 1. And so finally we get c sub k is equal to 8 minus 2k over k squared c sub k minus 1. Going from this step to this step, I just use the fact that the negative of this numerator is equal to this numerator. So here's what we have. C sub k equals this stuff in terms of c sub k minus 1, and this holds for all k greater than or equal to 1. So here's a Python program to compute at least a partial sum from that infinite series and also to plot it. This is the function that calculates y sub 1. Here I called it f. Over here is the main program, and down in this main program we will see at this stage that we call that function f and compute its value at some value x, and then we're going to append that value of y to a list which we call y list. So let's see what's going on here in just a little bit more detail. In the main program, we've set the number of coefficients equal to 40. That means that in this series that we have up here, we're going to let this sum go from actually k equals 0 to 39, which will be 40 terms in this series. That partial sum should hopefully be a pretty good approximation of the infinite series. So we'll set r equal to minus 2. That was the solution to the indicial equation. We'll start off the c list, the coefficients c sub k's, with c naught equaling 1. We know that c naught has to be not 0, and we can pick it to be any non-zero number actually, and it will just affect what multiple of this solution function that we'll get. Easiest to work with is set it equal to 1. And then we have a loop here for k in the range from 1 to the number of coefficients. Append to the list c the next c sub k value, which is computed by that recursive formula, 8 minus 2 times k divided by k squared times c sub k minus 1. So we append that to the list c. After this loop finishes, we have a list c with 40 numbers in it. Just to check what the values of c are, I put in a print statement here. You can run this yourself if you want to and see what c was. That was kind of a debugging maneuver. And now we need to figure out how to plot this function. So I'm going to set up two empty lists, x list and y list. I'm going to look at values of x in the interval ab, which goes from 0.4 up to 2. I'm going to evaluate this function up here at 400 points, and I'm going to do it on an equally spaced number line with x sub 1, x sub 0, x sub 1, x sub 2, all the way through x sub, I guess, 399. And the delta x that we'll use to get equal length subintervals is going to be b minus a and b were these numbers up here, divided by the number of points. So that will give us a pretty small delta x. Then for k in the range num points, this means that we'll let k go from 0 to num points minus 1. X will be a, the beginning point of this interval, plus k times delta x, and I'll append that value of x to x list. We'll then compute y equals f of x, and here we had to pass it besides x, the coefficient list c, the indicial equation solution r, and the number of coefficients we want in our partial sum. After we compute this y corresponding to that value of x, we append that to y list. After this loop is finished, goes through 400 times basically, we then plot x list versus y list. Now up here we have the definition of f. F of xc are num coefficients. We're going to compute partial sums here. by initially setting sum equal to 0, and then for n in the range of num coefficients, sum will equal sum plus c sub n times x raised to the nth power. And remember that the Frobenius solution has x to the r times this series. So after this partial sum is computed, we're going to multiply sum by x raised to the r power, and that will be the output of our function, and f will return that output value. So when you're typing in this program to Python, you would put this part of the code first, this part of the code second. Also, when you run this, you need to import matplotlib.pyplot because that's going to be used to do this plot over here. I called this thing just PLT to give it a short name, and so from that library, which I called PLT, we call the plot function and give it the values of xlist and ylist, two lists of numbers which it can point as pairs of numbers, coordinates of points in the plane. So here's the output of that program, plotting the points on what we call the function f of x, which corresponded to our solution y sub 1 of x to that differential equation. It's a nice smooth curve like this. We plotted it from x equals 0.4 to x equals 2.0, and as we can see, the y1 values on this curve go from almost 28 all the way down to about 12. To check our Frobenius solution for y sub 1 of x, we're going to find a solution y sub 1 of x again by using Euler's numerical method. So here's what we'll do. We already have a program that will produce a Frobenius solution, a series solution for y sub 1 of x. And so we're going to use that Frobenius program to estimate the values of y sub 1 of 0.4 and y sub 1 prime of 0.4. So we'll use our series to get these estimates. Once we have these estimates, we'll consider them initial conditions for an initial value problem. So then we will use Euler's method to calculate the numerical solution to that initial value problem for y sub 1 of x, and we'll plot that numerical solution that we got from Euler's method. We can then compare it to the solution that we got using the Frobenius method. First, we will use our Frobenius program written in Python to estimate the initial values y sub 1 of 0.4 and the derivative y sub 1 prime of 0.4. So here is the extra Python code added to our last program to compute y of 0.4 and also the derivative of y with respect to x evaluated at 0.4. Remember, in that program, the value of y at 0.4 would be calculated using our function f, our Python function f, at 0.4, c, the list of coefficients, r, and the number of coefficients. And then we can approximate the derivative of y at 0.4 by calculating y of 0.41 minus y of 0.4 divided by 0.01. And here's the code that does it. we can let x be 0.4 and calculate value of y using that value of x. The derivative of y with respect to x is approximately equal to f of x plus 0.01 with those same other parameters minus f of 4 with those same parameters divided by 0.01, this stuff right here. And then we'll print out the value of y and the derivative of y with respect to x, and the values we get are y is 27.783, the derivative of y with respect to x is about minus 65.368. And secondly, we will use Euler's method to calculate the numerical solution to the initial value problem for y sub 1 of x, and we will plot it. So what we saw was we're going to solve this differential equation with the initial conditions that y1 of 0.4 is 27.783, y1 prime of 0.04 is minus 65.368. Just for convenience, I'll call the function y of x instead of y1 of x. So we're going to use Euler's method to numerically solve this initial value problem. Y double prime plus p of x y prime plus q of x times y equals 0, where y evaluated at a is some number w naught, y prime of a is another number which I'll call z naught. Here, p of x is 5 plus 2x over x. The q of x is 4 minus 2x over x squared. So the program we're going to write is a little bit more general than just to solve this equation. We want to be able to solve any equation of this form with given initial conditions. Now the rest will be very similar to what we did before. Let's let w equal y, and you can see why I used w here for y of a. And let z be the derivative of y with respect to x, so you can see why I used z naught to be y prime of a up here. Well, in that case, the derivative of y with respect to x is equal to the derivative of w with respect to x, since y equals w. But the derivative of y with respect to x, remember, we called z. So this derivative equals z. If we want the derivative of z with respect to x, by just differentiating this with respect to x, we get dz dx equals the second derivative of y with respect to x. So this second order homogeneous differential equation can be written as the derivative of w with respect to x equals z, which is this equation right here, and then the derivative of z with respect to x, which happens to be the second derivative of y with respect to x, equals what? Well, from this equation up here, it's going to be minus p of x times y prime, which is z, minus q of x times y, which is w. Just taking these two terms by subtraction, getting something on the other side here instead of 0. Okay, and then in Euler's method, just as before, we're going to pick a small delta x greater than 0. I'll let x naught be 0.4, let y naught be 27.783, and let z naught be minus 65.368. And then in a loop, we're going to let x sub k plus 1 equal x sub k plus delta x. W sub k plus 1 will be the old value, w sub k, plus delta x times how much w changes with respect to x. And so we can write that as w sub k plus delta x times z sub k. And similarly, z sub k plus 1 is z sub k plus x times the derivative of z with respect to x. But the derivative of z with respect to x, according to this, is minus p of x sub k z sub k minus q of x sub k w sub k. So here is a Python program to implement Euler's method. Note here we define a function p of x to be 5 plus 2 times x over x, and that was the p of x in our differential equation. We define q of x over here to be the q of x that we have right here in our differential equation. And I'm going to plot the solution function y sub 1 on the interval starting at 0.4, ending at 2. X list, the first value of x is going to be a, which happens to be 0.4. We found that from our initial conditions, y naught was 27.7833, z naught was minus 65.3680. So these are the first numbers in the W list and the Z list. I guess you could say they're the zeroth numbers in those lists, since the index starts with 0 for a list. We're going to graph using 100 points. Delta x will be b minus a divided by that number of points. And then, just as we saw earlier, we'll let x equal x plus delta x, but in this case x list dot append x list sub k plus delta x. So what happens is we take the kth value of x, we add delta x to it, and then we add it to the x list. Similarly, for the w's, we take the kth element from the w list, add to it delta x times the kth element from the z list. That is basically w sub k plus delta x times z sub k here, equaling w sub k plus 1. We also augment the z list by the next z value using this formula over here. And since we defined p and q already, we can just use them in here. P of x list of k times z list sub k plus q of x list sub k times w list sub k. And then after we have gone through this loop about 100 times and computed x, y, and z values, we will plot the x list versus the w list, which are basically the x values and the y values plotted against each other. Here is the output of that Euler program, the plot of y sub 1 of x, our first solution to that differential equation by using Frobenius series. This looks almost identical to the graph that we got by plotting the series itself rather than using Euler's method. So we got the same graph as far as the eye can see from both methods of solution. So we're probably pretty sure at this stage that the solution we computed is correct. So here's what we do. For y, we substitute w of x, y1 of x into our differential equation. So we have the second derivative of this plus p of x times the first derivative of this plus q of x times this equals 0. Now here's what we know. We know that y1 satisfies a similar homogeneous differential equation, and we want wx times y1 to also satisfy that same differential equation. If w of x were a constant function, then the next solution we get y2 of x would not be with y1 a linearly independent set of solutions. So we're really looking for a non-constant function w of x that satisfies this equation, given that we know that y1 satisfies that equation. Okay, well, if you take the second derivative of w times y1, what you get is w double prime times y1 plus 2 w prime y1 prime plus w times y1 double prime. Then when you look at this next term, p of x times the first derivative of this product, by the product rule, this term is going to be p of x times the following stuff: w prime times y1 plus w times y1 prime. And finally, we have q w of x y1 of x, and I'll just copy that down right here, and that equals 0. Now, what's interesting is to look at what we have in blue here. W of x y1 double prime of x, I wrote it right here, plus p of x times this stuff, wrote that stuff right here, plus q of x times this stuff, I wrote that right here. And then we have all of the other stuff, which is this term plus this term, which we see here and here, plus this factor times this term, which we see here. Okay, so I now have this broken up into this part plus this part equals 0. Now, if you look at what we have up here, I was looking ahead in my computation. I have w of x as a factor in these three terms. Let's factor it out. So we have w of x times y1 double prime plus p of x y1 prime plus q of x y1, which is right here, okay? And so if you look at this, you say, hey, wait a minute, y1 double prime plus p of x y1 prime plus q of x y1 is 0, because y1 satisfied the differential equation that we're looking at, that homogeneous linear differential equation. So w of x times 0 is 0. So all you're left with is this stuff right here. And so this remaining stuff, which we have here, has to equal 0. Now, if we look at this, there's a w prime here, there's a w prime here, and a w double prime here. There are only first derivatives and second derivatives of w. The 0th derivative of w doesn't occur. So this is really a first order ordinary differential equation, kind of hidden. Let's let w prime be z. So w double prime is z prime. W prime here is z. W prime here is z. And so we have z prime times this plus 2z times this plus p of z times this equals 0. This is just a differential equation involving z prime of x and z of x. So here's what we have. This is the equation that we just saw. Let's rewrite this a couple of times, doing a little bit of algebra, I guess, at each stage. Here, we didn't do too much arranging, I guess. But if we look at this line down here, this equation can be written as y1 times z prime of x plus this times z of x. That came from here and here, okay, equals 0. Now, let's divide by y1 of x. So when we do the division on both sides of this equation by y1 of x, here we just get z prime of x. Here we get this stuff divided by y1 times z of x. When you divide this term by y1 of x, you just get 0. And now we have z prime plus this junk times z equals 0. We recognize that as a first-order homogeneous ordinary differential equation in z of x. Now, we know how to solve first-order linear differential equations, whether they are homogeneous or non-homogeneous. So at this stage, we can either use an integrating factor to solve this equation, or more easily, we can just use a little bit of algebra and calculus to solve this equation, since it's a homogeneous equation. Basically, I'm going to get z prime over z equals something and integrate both sides. Okay, so here's the equation that we just saw. If we subtract this term from both sides of the equation, and then divide by z of x, we can rewrite this as z prime over z equals minus this fraction which we had up here. Okay, but then if you look at this for a minute, here we have 2y prime over y sub 1's, and we can write that this way. And we have p of x times y1 divided by y1, and that's just p of x. So z prime of x divided by z of x equals this. Now integrate both sides of this with respect to x. The integral of z prime over z is just the log of z of x. Minus, and then the integral of y1 prime over y1 is natural log of y1. And we also have to integrate p of x with respect to x. So we get this. Now, take the exponential of both sides. E to this log x equals e to this stuff. But now, let's see what we have here. E to the natural log of z is just z. E to the minus 2 natural log 1 of y is just 1 over y1 squared. And it's multiplied by e to the integral of p of x dx with a minus sign there too. And so we get this. Okay, so then remembering that w prime of x equals z of x, so w of x is just the integral of z of x. If I want to find w of x, I just have to integrate z of x with respect to x. So the integral of this equals the integral of this. W of x equals the integral of all of this stuff dx. So here we have a function of x, here we have a function of x, and we're integrating this product with respect to x. We're finding the antiderivative of this function right here, this integrand. Okay, so then remember that we started by assuming that y2 was going to equal w of x times y1 of x, and we found out what w has to be so that this thing, y2, is also a solution to that differential equation. So multiplying both sides of this equation by y sub 1, we just get that y sub 2 of x is y sub 1 times the integral of this stuff dx. Looks like a fairly complicated formula, and guess what? It is a fairly complicated formula. However, if p is a fairly nice function, maybe we can make some headway with this. Y sub 1 we already have found. We used the Frobenius method to find that, and we found that it was an infinite series. So I guess the question now is, how can we put that infinite series for y sub 1 together, this together, integrate the whole thing, multiply it by a series, and maybe graph this function, y sub 2. You know, the whole idea is to find y sub 1 and y sub 2. We can graph them, we can use them to do other things. So we need, in our particular example, to find y2 of x by using this formula. So we know that y1 of x is the solution that we got by looking at the Frobenius series. So we need to evaluate e to the minus integral p of x dx. Well, p of x in our differential equation was 5 plus 2x over x, which can be written as 5 over x plus 2. So minus the integral of p over x dx is going to be minus the integral of 5 over x, which is minus 5 log x, minus the integral of 2 dx, which is just minus 2x. We can forget about the constants of integration. So e to the minus p of x dx is e to minus 5 log x minus 2x, which is equal to e to the minus 5 log x times e to the minus 2x. Now e to the minus 5 log x is 1 over x to the fifth. E to the minus 2x is 1 over e to the 2x. So multiplying these together, we get 1 over x to the fifth e to the 2x. So in that case, y2 of x is equal to y1 of x times this integral, and that's what we need to evaluate. So here is the beginning of the program written in Python for reduction of order of the differential equation and the solution for y2. Notice that we have from matplotlib import pyplot as plt. We need to import this for our plotting. Import math as mth. Math is another Python library that helps us to compute functions such as the exponential or the sine, cosine, those sorts of things. We have another function defined here, find c, and what this function does is finds the coefficients in the series solution for y sub 1, the solution that we got using the Frobenius series. Down here we have the function y1. We have seen this before, and we output x to the r times this sum. So we're outputting basically one of the partial sums times x to the r. R is the solution to the indicial equation. Over here we have something new, rj integrate. And what this is going to do is integrate a function g. This function g is defined in terms of coefficients in a power series listed in list C. The indicial equation solution is r. We're going to integrate g from a number a to a number t. Num coefficients is just how many coefficients are in this list C, and the number of points basically determines how many terms we have in the Riemann sum. So we start by setting x equal to a. We'll set delta x equal to t minus a divided by num points minus 1. Remember that we're integrating on the interval from a to t, and so what we're getting here are delta x, which is the length of the subintervals that we divide the interval a t into. Then we have a sum part of the program here. Partial sum equals 0 for k equals range from 1 to num points plus 1. X equals a plus k times delta x. Y is g of x with those other things that we need. Partial sum equals partial sum plus y times delta x. And after this loop is finished, we return partial sum. So what we have computed here is a Riemann sum approximating the integral from a to t of g of x dx. Here are a few more functions that correspond to the notation that we used on previous slides. We define the function z the way that we defined it before. We define w to be basically the integral of z, and we define y2 to be y1 times w. Over here we have the main program. We set the number of coefficients equal to 40. That's how many terms we'll have in our series solution. We begin our list with C0 equal to 1, a list with one element, C0 equals 1. We use find C to find the coefficients for our solution y sub 1. We let the number of points be 501 for plotting later. R equals -2 from the solution to the indicial equation. We'll let AB be the interval going from 0 to 4 point. AB is the interval from 0.4 to 2. Dx is just b minus a divided by the number of points minus 1, which is the number of intervals. And then we get ready to do some plotting. We construct an empty list, x list. We also construct another empty list, y2 list. And then we fill them up. For k in the range 1 to number points plus 1, x equals a plus k times dx. X list dot append x, the value that we just computed here. Y2 list dot append, and then y2 of x, with all of these other parameters needed for the computation of y2 of x. After this loop is finished, we have filled these two lists with values of x and y2. So we plot them, and we plot them putting a title there and plot.show. Just make sure that that plot is showing. This is nice to use if you're doing more than one plot in a program, so that you do get separate plots. For each show will produce one plot. Here is the graph of y2 of x found by that program. The program first found y sub 1 of x, and then used reduction of order, and the formula for y sub 2 of x that comes from reduction of order to plot this function. So now let's check our solution by using Euler's method to graph that second solution, y sub 2 of x. And in order to do that using Euler's method, we need an initial value problem. So what we'll do is use the solution that we just got to compute some initial conditions. What the value of y is at 0.4, and what the value of the derivative of y with respect to x is at 0.4. To make an initial value problem, we will add this code to the end of the last program. We'll let x be 0.4, and then we will compute y2 of 0.4, and also by a difference quotient, we will approximate the derivative of y2 with respect to x at 0.4. When we execute the program with this additional code, we get as an output y2 of 0.04 is 0. The derivative of y2 with respect to x at 0.4 is about 1.4731. So here is a Python program for producing a plot of the function y sub 2 of x. This uses Euler's method to consider the initial value problem, where we have y double prime plus p of x, which is here, times y prime, plus q of x, which is defined here, times y equals 0. We're going to plot that on the interval AB, which goes from 0.4 to 2. We'll start with an x value of A, which is 0.4, W, which is the same as y of 0.4 is going to be 0, Z, which is y prime of 0.4, is 1.4731. The rest of this program is exactly the same as we saw for an Euler plot, a plot using Euler's method for the function y sub 1, which satisfied a slightly different initial value problem, different initial conditions, but the same differential equation. We will plot the values of x versus w, which is y basically, with a title, which we can see up here, and then we will show this plot. So the plot of y2 using Euler's method looks like this. This agrees very well with the previous plot that we saw, which we got by using reduction of order. And we know that from what we have right here, the initial conditions, this y2 satisfies this differential equation plus these two initial conditions. So comparing the two graphs, this is the graph of the second solution we got to the initial value problem, starting with Frobenius's method and then reduction of order. And this is the graph we got of that same solution using initial conditions at x equals 0.4, and then stepwise numerically computing points on this curve. And as you can see, these two curves look the same. So to summarize, we have two linearly independent solutions to the differential equation. Y double prime plus 5 plus 2x over x times y plus 4 minus 2x over x squared, y equals 0. This is a plot of the function y sub 1 of x, and we saw that y sub 1 of x satisfied approximately these initial conditions down here. Our function y sub 2 of x satisfies the same ordinary differential equation, but slightly different initial conditions. So when we compare y sub 1 with y sub 2, what we have in both of these systems of equations, the same ordinary differential equation here and here, but different initial conditions. The initial values here are not the same as the initial values here. So when we're finding two linearly independent solutions of this one differential equation, second order linear differential equation, the two functions that we have for the linearly independent set of functions just differ by the initial conditions. So let's recall some important points from this lesson. First, our solution y sub 1 of x was given by a Frobenius series. We did the calculations to find this Frobenius series. We used Python to plot this series and thus see a graph of y sub 1 of x. Our solution y sub 2 of x eventually was given by a formula. We got this formula by using reduction of order on the ordinary differential equation, and we were also able to plot this function y sub 2 of x by writing a Python program. We also saw that by determining initial conditions for y sub 1 of x and y sub 2 of x, we were also able to plot both of these solutions by using Euler's method. we had to find the initial conditions so that Euler's method could be used. We saw the results of this, the two graphs, agreed, at least visually, with our previous results. Thank you for sharing your time with me. I hope that you enjoyed this lesson.